electromechanical actuation system using Simulink, and the output data we have analyzed. And also some of the students have already done the frequency response analysis using sinusoidal sweep command, and then thereafter analyzing through Fourier series integral, finalizing the finally getting the frequency response with respect to the fundamental harmonics of the output. And also we have just gone through some simplified versions of various nonlinearities in the actual system. But then I mentioned that the nonlinearities that we are realizing in Simulink block simplified versions, and definitely we have to go through the actual model of the nonlinear characteristics, and that we will carry out using MATLAB. So prior to going to MATLAB, what we will do is first we will create a equivalent MATLAB integration and simulation program, which is equivalent to the Simulink version. The normal procedure that we follow in the development of any software or simulation is, first we will analyze the linear system using analytic. For example, here the total closed loop EGC system, we can take the transfer function with any input to any output. Once transfer function, the transfer function can be analyzed using standard commands in MATLAB, which is directly using analytic expression for the step response as well as frequency response. That is based on the inverse Laplace transforms as well as the Bode plot commands, etc. They are directly using the analytic expression for both step response and frequency response. You have already studied how you can get the step response of first order systems, second order systems, expressions you already have. So such expression will be directly used. So
sir, are you sharing any screen?
No, I am going to start only. Now I am only discussing. After that only I will come to sharing. Okay, you are able to hear me?
Yes, sir. Yes, sir. Okay.
I not started the screen sharing mode. Hence, we will be first concentrating on analytic expansion of step and frequency response. This is followed by Simulink simulation of the same thing. So you can always compare the step response obtained from Simulink and step response obtained through analytic MATLAB expression. Similarly, frequency response obtained from Simulink we can compare with the analytically obtained Bode plot response from MATLAB. Then the third phase is we directly do numerical simulation in MATLAB by directly writing codes in MATLAB. The MATLAB is having some numerical integration routine called runge-kutta method, which I will be discussing today. And we'll be comparing the MATLAB response with the Simulink response and ensure that your numerical integration routine is correct. After that, we use different nonlinearities one by one in the MATLAB simulation program. When you introduce each nonlinearity, you have an expectation. It should affect or change the response compared to the linear system response. And accordingly, we will be validating the response and subsequently we'll be adding more and more complexity. And this is how we normally develop the simulation. So let me first go to the screen sharing mode. I hope Abhilash has joined. So are you able to see in the screen now? Hello?
Yes, sir.
Okay.
Yes, sir.
All right. Okay. This is the portions for today's class. This matter will be shared to you. This numerical simulation of nonlinear mathematical model of electromechanical engine gimbal system using MATLAB and validation of the same with Simulink model. Whatever Simulink model you already developed for the previous sessions, like linear model or simplified versions of nonlinear model, that can be used to validate the new MATLAB-based direct coding program. That is the objective. So is to learn the algorithm and coding of the numerical simulation program for a typical servo system in MATLAB and to validate the same by comparing the results with Simulink model. Theory, the nonlinear mathematical model, the Simulink model corresponding to nonlinear mathematical model of electromechanical EG system used in session 2 of the lab. What I mean session 2 is the previous sessions where we have completed the linear as well as basic nonlinearities. Nonlinearities considered are integral limits associated with PI controller, supply voltage limit, and simple form of motor Coulomb friction, as well as actuator stroke limit also you have. In this MATLAB program that we are going to develop, what we'll use is numerical integration routine already available in MATLAB. There is the runge-kutta methods. They are a family of implicit and explicit iterative methods, which include the well-known routine called Euler method, used in temporal discretization for the approximate solutions of ordinary differential equation. These methods were developed around 1900 AD by German mathematicians Carl Runge and Wilhelm Kutta, this runge-kutta method. The most widely known member of runge-kutta family is generally referred to as RK4, the classic runge-kutta method. There are Kutta algorithms are there, but this is a good enough with respect to computational complexity as well as with respect to accuracy. If you go to higher order runge-kutta method, it will become computationally more complex, but accuracy will improve. But if you go lower order, computationally it will be fast, but accuracy will decrease. So RK4 is accepted as a generally good model, a compromise between accuracy as well as computational complexity. The problem can be stated like this: numerical integration problem. This is an initial value problem. It can be stated as y dot is equal to f of t y, yt0 is equal to y0, where y is an unknown scalar or vector function of time t, which you would like to approximate. What is given is, we are told that y dot and the rate at which y changes, that is known, and that is a function of t and y. At the initial time, the corresponding value of y is y0, the function of f, and the data t0, y0 are given. So what I'm telling is, y is a function of time t. It is evolving, but it is a dynamic function. We are not exactly given what is the function y of t. Instead, what is given is the rate of change of y with respect to the current time as well as the current value of y. If you know the current value of time t and the current value of y, we know what is the rate of change of y. From that, we have to find out what is the value of y in the next instant. So the current value of y gives only the slope of y not directly the next value of y. So it is our job to find out. We have to predict or we have to estimate, compute value of y in the next instant given the value of y at that current time. But because this is only mentioning about the slope of y, definitely to uniquely express it, we require the initial value of y at a specified value of time, initial value of time t0. So it is an initial value problem. At time t0, value of y0 is known, and how y changes with respect to both time and y is also given. So it's a typical integration problem. If analytic for the solution is available, it is well and good, but in general, it is a nonlinear function. Nonlinear differential equation, there is no generic method to solve it. That is why we have to go for numerical integration. So this will be our problem of engine gimbal control, EGC problem. Also, we can finally state in this form. That's what we are going to do, where this y is not a scalar, but it will be a vector. Probably what we do is we find out what are the state vectors, state space formulation we will go for. And since the system is being nonlinear, it is a nonlinear state space equation. If you represent the state of the system by, say, x, it is an n-dimensional vector. Then x dot you can express as a function of time t and the current value of x and the initial value of system. We will integrate, numerically integrate the states x then to find out how the states are evolving. This is the problem. Any doubts so far? Okay, now we will see how we can do it in a numerical way. The first step for numerical integration is to select the integration step size. Truly, it is actually it is a continuous time process. But in computer, what we do is we are using digital computer with a digital computing software to do it. So finally, everything has to be converted into digital process. The continuous time process, we have to convert the equivalent digital process. There involves with what interval we will discretize, digitize the process. When we do this, is definitely an approximation. So smaller the interval of digitization, discretization, better will be the accuracy. So we have to select what is the interval. Here, the simulation interval is called h, small h. The objective of numerical integration is to reproduce the continuous time solution with minimum error due to discretization. A rule of thumb to achieve the same is to select the simulation frequency f of s in hertz as at least 50 times the maximum model frequency of the system dynamics to be reproduced, and interval is equal to h is equal to 1 by f s. Suppose we have a closed loop control system having a bandwidth of 5 hertz, for example. When we say 5 hertz, that doesn't mean that we are bothered only up to 5 hertz. If it is not having any other frequency component, when I say frequency component means when we model the system, there will be so many modes will be there, flexible modes will be there, structure, control structure, interaction, resonant modes. Any practical system is flexible. It will have modes of resonance like first mode of resonance, second mode of resonance, etc. Normally these resonance modes will be keeping quite away from our rigid body bandwidth 5 hertz, but still cannot be far away. If we are keeping far away means the design is not optimal. Normally in engine gimbal control system in launch vehicle, such resonant modes will start from twice the bandwidth onwards. If bandwidth is 5 hertz, the resonant modes will be some 10 hertz, 15 hertz, 20 hertz, like that. So the designer, the simulation man has to answer up to what resonant mode he is interested. Suppose I'm interested up to resonant mode up to 25 hertz. Then the 25 hertz in the system also should be reproduced in the simulation. That means here what I told, 50 times of 25 we have to take as Fs. If it is 20 hertz, 20 into 50 is 1000, 1 kilohertz you will get, Fs will be 1 kilohertz, and hence the sampling interval will be 1 by 1 kilohertz, that is 1 millisecond. This is the rule of thumb. This should not be confused with, there are other critical frequencies associated with control system. One frequency, some of you may be aware, it's called sampling frequency with respect to communication. That is, if you are sampling some particular signal, the minimum sampling frequency without losing the message content is twice the message frequency. It's known as Nyquist or Shannon's criteria, but that is being used in digital signal processing by your electronics and communication engineering friends, ECE friends. You will not be normally using that. But for the sake of understanding, you should keep that. That is, if a message is to be sampled without loss of information, the minimum sampling frequency is twice the sampling, twice the message frequency. Another is the frequency associated with digital control system or sample data control system. The sampling frequency for control, that is even higher. It is not the, we have to do simply conserving the message. We have to ensure that the sampling process will not introduce unnecessarily phase lag in the system, and hence that requirement is even higher. There the criteria is the sample and hold SOH process should not introduce unnecessarily lag. Suppose phase margin is 45 degree in the closed loop control system. The additional phase lag due to sampling and holding should not exceed some 2 to 3 degrees. That is a criteria. But here the criteria is not even that. Here we are trying to reproduce an analog system dynamics using digital simulation. There the requirement is even much more. That's why we are going for 50 times the maximum frequency to be reproduced. Okay. Now, any doubts?
Sir, sir, you told about the bandwidth, right? The resonance frequency is more than the bandwidth of 5 hertz. Like, sir, what is the physical meaning of this bandwidth? Like, after with the solution becomes accurate, or like, what is the meaning of this bandwidth?
Say bandwidth we refer to is minus 3 dB bandwidth. Say finally the control system you are designing to be a tracking system, right? It has to track input command. For example, PS4 EGC system, it has to gimbal with plus or minus 4 degree. And already you have specified the bandwidth as say 5 hertz. That means the digital autopilot is giving a command to the engine gimbal control system to oscillate the engine at 5 hertz with say 0.4 degree amplitude. The control system should do it. That is, the output deflection should track the command. But exactly nobody can track. There will be an attenuation with respect to amplitude, and there is a phase lag with respect to the phase. So minus 3 dB is one specification. With respect to amplitude, the amplitude of deflection will be 1 by root 2 times the amplitude of the command. And if you specify the bandwidth as a minus 90 degree bandwidth, what does it mean is the phase of the deflection will be lagging behind the command phase by 90 degrees. So these are the two typical bandwidth specifications. But now in our lab, we are only using minus 3 dB bandwidth. Any doubts so far?
No, sir.
Okay. That's a bandwidth, but control structure resonant frequency is coming from the plant dynamics when it interact with the mounting system structure, mounting brackets and all. That is a characteristic of the plant dynamics. Normally that will be of the order of 2 to 3 times the bandwidth. That's how we design the system. We can design the system with structural frequencies 10 times, but that is not an optimal design, unnecessarily ruggedizing the system. Control requires that the structural frequency should be away from the bandwidth by at least 2 times. That's sufficient. That is how I told. Then for simulation, we have to simulate that structural frequency also, because that is also a part of plant dynamics. So we have to take 50 times of the maximum structural mode that you have to simulate. That is a concern. I hope all of you are clear with respect to that point. Okay. Now we are going to the numerical integration routine. You see, this is the runge-kutta method RK4. I already told that our basic problem was we are having y dot only as a function of t and y. So our job is to find out, we have to predict future values of y given the current y. So suppose that we start with nth sampling interval. This is a sequential process. So given nth sampling interval, how you will predict the sampled value of the state at n plus 1th interval. This is done by a 4-step process in RK4. So 4 corresponds to a 4-step derivative evaluation is there. And once that is over, you will estimate yn plus 1 using this, and tn plus 1 is advanced such, and n is varying from 0, 1, 2 onwards. So first we will start with the initial condition, that t is equal to at t equals 0. So tn plus 1. So n is equal to 0 means t0. T0 is equal to 0, for example. That is a good value we can start with. Then t1 will be is equal to h, that is 1 millisecond if you are telling. T2 will be 2 milliseconds, T3 will be 3 milliseconds and so on. And y0 will be the initial value of all the states. Suppose the gimbal is at null position with 0 velocity. Then what are all the states involved? You know that the states are deflection is one state, angular velocity is another state, and states of the controller. If you are using a PI controller, integrator is having a state. Suppose you are using a low pass filter. Low pass filter, if it's a first order, it will have an internal state. If it's low pass filter second order, it will have 2 states. If you are using a sensor, a demodulator filter, so LVDT is normally associated with a second order filter that will have 2 states. So all the states we have to initialize, and a good value is normally 0 value. It starts from absolute rest with respect to all mechanical as well as electrical parameters. But if you start with a deflected condition of the nozzle, then you can give a finite value for the deflection. Suppose you start with a finite velocity, you can give that as the initial condition. So that is possible. Now I am going to explain what is S1, S2, S3, S4. This S stands for slope or the derivative. I 1 to 4 represent intermediate slopes of or the value of y dot is approximate like this. S1 is equal to f of tn yn. If we start directly, see, this is an expression. What is f? I already told. F is nothing but the derivative of the function. It gives the current instant slope. If you know the current time instant and the current value of y, it gives the instantaneous slope of the function slope of y. That we assume that the same slope is applicable for the next interval, say up to half of the 1 millisecond, h by 2 up to h by 2, it is applicable. So what we do is we use that slope and extrapolate the value of y, say yn plus h into s1 by 2. What does it mean? We are using yn as the current value, and we assume that yn is evolving like a straight line ramp function with a constant slope, and that slope is applicable for the next h by 2 interval. So this is called Euler prediction. This is the simplest numerical integration method. This the simplest one. We assume that it proceeds with the same slope at the nth instant, and we assume that slope is applicable up to the next half interval. Actually, you know, the slope is varying as a function of the value of y, but we are approximating in digital domain. So we assume that slope is throughout same up to the next half interval. So we find out that is a first prediction based on Euler assumption, and we get effectively the value at time n plus h by 2, and you get the predicted estimated value of the system yn plus h plus this next instant n plus half interval, and we evaluate the slope using the function f. Then this new slope we are used for predict next time. That is, again, we are predicting the new value of y at the n plus half interval, that is n plus h into s2 by 2. That yn plus h into s2 by 2, that we take it as the new value of the yn for the next half interval and evaluate the new slope. Then we make use of this third slope. We make use to predict for the full interval, h into s3 by 2 instead of h by 2 for the full interval. Thus we get Euler prediction for the full interval. Thus we get the interval, the value of the y at n plus 1, that is tn plus h, that's the time. We get s4, and we find out what is the slope. So all these slopes we get, then we take the average of the slope. We get double weightage for the intermediate thing, because we this is the runge-kutta logic of prediction, and a single weightage for the first and the last, and finally, you know, 1 plus 2 plus 2 plus 1. This total weightage is 6, so divide by 6 to get the average slope. This is how a runge-kutta prediction goes. And if you can refer to various textbooks for getting further information on this. And we make use of this formula to write a program. So we will be writing two simulation program. One is integration routine and derivative routine. The simulation program MATLAB is the integration routine called int-egc1.m, that is integration routine. And program start with global command. I will explain with respect to the program. Then there is a derivative routine and the procedure. These procedures will be explained by Mr. Abhilash in the class. So I will just show you what is the structure of integration derivative routine. Can you see this integration routine? This program will be given to you, because to start with, you should get a reference program. We'll be sharing the program. It is very important to give proper name. INT means integration, EGC, changeable control, the first version. This integration routine is for PS4A system. First one is command clear all. We have to clear the workspace. Otherwise, when we execute multiple commands repeatedly, the previous some variable values will be there in the MATLAB workspace and will create confusion. So clear all, everything. So MATLAB workspace is clear. Then we declare some global command. what does it mean is these variables will be global with respect to all the programs wherever we are declaring it as global. In the next subroutine, derivative subroutine also will have the same global statement. So if you initialize KT, KB, etc. in one of the program routine, that will be that value, initial value will be carried to all the programs. And it's a safe practice to initialize all these variables in the integration routine itself. If you initialize the variables in multiple programs, when you change the value, you will sometimes forget to change in one program, only change in the other program, and there will be confusion. So you initialize all variables in the integration routine and declare it as global, so that you need to declare every variable as global in every program. Whatever variables recorded in a particular program, that only you have to declare as global in that particular program. But in the main program, you declare all the variables which we want to pass on to other programs as global and proceed. This KT, KB, these values already you know, and we are evaluating K1, K2, KI, integrator gain, derivative gain, etc. Finally, now only we start the numerical simulation. So far, you have been using Simulink for this. You only found out the values of the gains, and these gains are directly passed on to the Simulink. Now, we are replacing the Simulink with our own runge-kutta method. Some flags you can initialize. Now we are not using the flag. For k is equal to 1 to 1000 intervals we are simulating. For example, if you are using your sampling interval as 1 millisecond, then 1000 into 1 millisecond is 1 second. You will be simulating for 1 second. Likewise, you can change. And the sampling interval you have to declare in this main program as h. You can see that h is equal to 0.001. That is 1 millisecond we are declaring. Then what next? This is the once we start this, the command, simulation command, external, that I am declaring VR is equal to VR max. Reference into sine omega t, R for reference, omega. You can see you can earlier initialize omega is 2 pi, that is 1 hertz. VR max is equal to 1 volt. And any value of VR you can corresponding to the sampling interval. K is determining the current time. There you can get, and we are declaring this. And this S1, S2, S3, S4, these are the various slopes we already found out in that runge-kutta method. Then you are taking the average of that one, then updating the value y is equal to y plus h into s. Here only we are updating the states, the time we update, the command we update, and any limit we are going to apply on the system states we apply here. Say 13 volt we applied for the some integration output there, y of 1. Here y of 1 is nothing but the first state, which is the integrator state. And that is what we are limiting here, as we did in the Simulink. And finally, we are stacking all the variables for future plotting. Small y, t, and the command, all these things, we stack it as a vector. And finally, you can save it using save command, which can be retrieved later. Along with this, we have the derivative routine. This is a derivative program. And every step of the runge-kutta algorithm, to find out the slope, we will call this derivative routine. There also you see the global is there. Then from what we passed on is the current value state, which we refer to as y here I am getting as x. What is der PS4x? How we call from the previous program? You see, here it is called as der EGC1. Okay, that I have to, there it is der PS4. We have to update it, correct it. I will, because it came from 2 different times. Actually, we have to write as der PS4, and der PS4, then automatically it will call the der PS4. So the name of the derivative routine you have to give in the integration routine. And it will execute the derivative. How we find out various state derivatives, all are stated here. Xi, first we'll initialize all the states, whatever the same y is coming here as x, and initialize and execute the PI control. Then the saturation limit is there. Then followed by that we have the dynamics. That is x angular velocity as well as deflection. That derivative expression based on various omega and theta, all these things we get. This is how we do the simulation and again come back. And if we execute, I will show how we'll execute this in the MATLAB itself. I will show that. Suppose the same integration derivative, if I run it, the final result we are obtaining. There is an output deflection as a function of time t. This we have to compare against the simulating output and validate the MATLAB is working. So I will be giving you the MATLAB program as well as the material and sharing with you. One thing for this Friday, today, as well as next week is required to complete the ongoing activity. So this will be starting only in the next week. And next week, Friday, we don't have class because you have Qs. That's why I had taken the theory for the next week today. I will be sending you this material. Any doubts so far? Okay, we can leave. Class is over.
Sir, you told, sir, suppose that the resonance frequency, it falls close to 5 Hz. So how will we change our this bandwidth then? We'll decrease it by to 2.5.
No, it is not like that. That is how when this is a part of the system design. See, when somebody is designing the rocket system, this is a very important thing because the mission requirement from the control and